As usual, first I spent usually 15 minutes reviewing the major points of new material. So I'm going to do the same this time. So again, it's all based on chapter 12. Yeah, by the way, can you hear me at the back? Good? Should I crank it more? No? It's fine. So what? We started this chapter with the idea of the center of mass. It's just a very sweet spot in any mechanical system, and which has a few amazing features which can be used to simplify calculations, like for example finding the potential energy of a rigid object, right? Or calculating the gravitational torque of a rigid object. So we introduced the idea of center of mass. Cm stands for the center of mass, you remember, right? So we introduce it in this way. R of the center of mass equals m1 r1 plus m2 r2 divided by the total mass. Okay, I wrote it down for the case of two masses, right? Of course, you can continue this. You can make this formula complicated by adding more and more masses. Then next, we introduce rotational kinetic energy. All right, K rotational. So if you have an object which is spinning or rotating, it's a motion. Rotation is a motion, so it means that we can introduce kinetic energy, which is energy of motion. So we introduce it in this way. Actually, we derived it. Right? Moment of inertia times angular velocity. It can be easily restored if you remember kinetic energy for translational motion. 1/2 mv squared. You just need to replace mass with its rotational equivalent, which is moment of inertia. And instead of translational velocity, you need to introduce angular velocity. So if you remember one formula, you should be able to restore this immediately, right? But again, it will be given on the formula sheet. All right, so let me frame this. It's important. We introduce moment of inertia. And I moment of inertia. And by definition, moment of inertia is for a point mass. So if you have, this is axis of rotation, and let's say you have a point mass m position at the distance r from the axis. Yeah. Guys, you're free to move back and forth, right? Okay, yeah, I will try. Usually, I'm trying to fit all the review in this piece of the board, part of the board, right? And sometimes I ran out of space, that's why I'm writing it smaller. Okay, let me make it slightly bigger. So, let's say we have a system which is spinning or rotating around this axis of rotation. And let's say we have mass m at a distance r. So then, moment of inertia is mass times square of the distance from the axis of rotation. That's moment of inertia over point mass. Let me reduce this. And for let me write it. It's for a point mass. It's a rotational equivalent of mass. So mass was enough to describe translational motion, but in order to describe rotational motion, information about the mass is not enough. You also need to know how that mass is distributed relative to the axis of rotation. And for a rigid object, a rigid object, table 12.2, but of course you're not going to have books on the exam. So whenever a moment of inertia for a rigid object is needed, of course I will give you in the problem, right? But of course you need to understand what is R in that formula, or what is L in that formula. For example, if it's a rod, L it's the length of the rod. If it's a disk, R it's the radius of the disk. Of course I'm not going to give you explanations what each symbol means, right? But of course, every time if you have a rigid object in the exam, moment of inertia will be given. So you don't have to memorize those, right? It will be just waste of time. Okay, for a rigid object, it will be given again, I started writing slower. Then, very important, right? A cross product. Let's refresh a cross product. Cross or vector product. No, let me just write cross product. Cross product. So if you have, for example, cross product of two vectors, A and B. Right. Let's say vector A this way, vector B this way. So in order to calculate this cross product, let's say it is C. So the magnitude is, which we wrote here. So the magnitude of this cross product, it will be magnitude of A and magnitude of B times sine of angle between these two vectors, sine of angle. That is the angle. So in order to find angle, you remember what's the rule. Position their tails at the same point, and the angle, which is smaller than 180 degrees between these two vectors, is the correct angle for calculation. Then, right-hand rule. In order to find direction, you have to use the right-hand rule, which I usually call number 1. So what is the rule? You take, first of all, this C must be, it's basically a mathematical tool. You just need to learn how it is introduced in mathematics, right? Don't try to find logic. It just helps to explain physics. It helps to explain what we see around us. So, by definition, C is perpendicular to both of these vectors. So it means that C must be either out of the board or into the board. So you already restrict yourselves, direction to two possible directions. And then apply right-hand rule, right? So first align your hand along the first vector A, first vector in the product, right? And then orient your hand in such a way so that you can naturally bend your fingers towards the second vector in the product. So I have to position my hand first like this, then bend my fingers towards B, and my outstretched thumb gives me direction for the C. Or like my instructors, right, when I was an undergrad student, taught me this way. So they told me, right, grab this second vector B, position it to the end of the first vector. So now you see this clear flow. First this way, then that way. So and then just curl your fingers in that direction, giving you direction of the C vector. But that's how I was taught. Books usually explain this way: align, bend. Okay. So in this case, C will be into the board. So in this case, C into the board. Which sign do we have to use? It's a cross, right? You remember cross dot. So vector C. So on the exam, you might need in a couple of places. In physics 2, in the second half of the semester, we will be using this cross product a lot. When we get to the magnetism, right, if you're going to take physics 2. Right, so now, what's next? After that, let me separate this. After that, we went to, we started describing rotational dynamics. So we introduced idea of torque, angular momentum. So let's first introduce torque. Refresh. Torque. So by definition, so let me draw some object. Let's say this is a rigid object. And let's say this is the axis of rotation. Axis. And let's say the force is applied. Let's say force is applied at this point, right? F. So, by definition, torque is, where should I write? Well, I will write it here. So, tau, Greek letter tau. I know some of you are familiar with this Greek alphabet, but with time you will get used to it. Okay, so it's by definition, again, it's a cross product between R and F. Cross product. Right. So that's definition of the torque. And of course, what? Again, you can, in order to find the magnitude, you just use this. Right? RF sine theta, and apply right-hand rule to find the direction. So where is R? R is this. It's a position vector from the axis of rotation, or the origin. In this case, I will position origin at that point, and to the point where the force is applied. Now, how can we calculate magnitude? Magnitude, let's say, magnitude of this torque. So magnitude is magnitude of the first vector, magnitude of the second, times sine of angle between them. Strictly speaking, I'm talking about this angle theta. Or, as I told you already several times, we can use this trick, these two tricks, which can simplify our calculations slightly, not that much, but slightly. So we can use, if you combine r and sine theta, you can get what is called r perpendicular. What is r perpendicular in this case? You draw the line of force. You see this force? And we're going to use this trick several times in today's exam review session. So I will draw this line. It's called line of force. Line of force. And r perpendicular, it's the shortest distance, the perpendicular distance from the axis of rotation and the line of force. I showed you, I proved that in the lecture. You can open, I think it's a lecture 20, you can open a few graphs, right? You can see that. So in this case, r perpendicular, let me use this. It's this distance. This angle is 90 degrees, so that is r perpendicular. Sometimes in the problem, if you see the diagram, you can see sometimes this r perpendicular immediately. As a result, it saves time. It saves time. F. Or you can use, or tau can be, if you combine F sine theta, you will get R times F perpendicular. What is F perpendicular? You see this line of R, right? And F perpendicular will be just a component perpendicular to that direction. But we use this less often. So in this case, this will be F perpendicular and full R, or in this case, R perpendicular and full F. Right. But again, most of the time, we're going to use this. It's just a small shortcuts in terms of calculations. Now, let me frame this because I'm going to use it several times. Next. Then we introduced angular momentum. So after this, we introduced angular momentum, A and G momentum. Don't complain that my N and my U looks the same, right? So I will never be able to, no, probably I can fix it. So angular momentum, so by definition, it's L equals R cross P. One of the fundamental quantities in physics, right? When you want to describe rotational dynamics. It's basically it's a rotational equivalent of linear momentum. Linear momentum was enough to describe translational dynamics, linear dynamics, right? Translational motion. But again, if you go into the rotational dynamic stuff, which is spinning, rotating, just the linear momentum is not enough, right? So now you have to use angular momentum. And look, can we use these tricks to calculate angular momentum? From the mathematical point of view, there is no difference between this and that, right? It's exactly the same cross product, but of course instead of force, now you have to use linear momentum. But in terms of calculations, you can use these safely, right? Let me write over here above. It can be used to calculate angular momentum as well. So all these tricks can be used to calculate angular momentum. And in 10 minutes we will look at the examples. Yes, so that is definition of angular momentum for a point mass. Okay, let me write it. For a point mass. Now, how can we calculate angular momentum of a solid object, rigid object? Again, it can be shown mathematically. We did not do it, of course, because it's for advanced level class. Angular momentum is I omega. That is for a solid object. Solid object or rigid object. So whenever you see a point mass, if you want to know angular momentum, you use this. If you see a rigid object, disk, rod, square, spinning or rotating, of course you will have to use moment of inertia, which is of course will be given for a rigid object, times angular velocity. Next, so this section of the review done. Let me separate it a second, right? Now, we introduced after that rotational Newton-second law. Rotational Newton-second law. In two forms. Right? So first, net torque acting on the object with moment of inertia I leads to an angular acceleration times alpha. So it's a first form of rotational Newton-second law. It's easy to remember because it's the structure is exactly the same like the structure of the translational Newton-second law. F equals ma. So what is the rotational equivalent of the force? Torque. What is the rotational equivalent of mass? Moment of inertia. And what is the rotational equivalent of translational acceleration? Angular acceleration. So the structure is exactly the same. You just replace linear quantities, translational quantities with rotational quantities, and it's all set. So it's a first form. Let me circle it in blue because it's slightly less general. And the most general form of the rotational Newton-second law, which you can apply for any rotating system at any point of the universe, at any moment of time. Net torque acting on the system leads to the change of the angular momentum. So if you apply torque over some period of time, angular momentum of the system will change. For example, right now the ball is stationary, there is no spinning, right? Angular momentum is 0. If I apply torque with my fingers over, let's say, 1 second, it starts spinning. So I change angular momentum, right? By applying torque over some period of time. As a result, angular momentum changes. So that's how you can read this rotational Newton-second law. So let me frame it. Right? This is general form. Now, yeah. Then we introduced conservation of angular momentum. Right, so let me write next bullet. Conservation of angular momentum. Angular, and this is annoying. Right, conservation of angular momentum. So what is that? If net torque acting on the system, system can be one object or many objects. If net external torque acting on the system is 0, then angular momentum is conserved. Justification of this is more complicated than the justification of conservation of energy or linear momentum. So on the exam, of course, I will never ask you to justify it. Because in that case, you will have to dive a little bit deeper, directions of the torque. No. If I give a problem on conservation of angular momentum, and I will definitely give a problem on conservation of angular momentum, right? I will just tell you, guys, use conservation of angular momentum, right? Without justification, because it's a little bit more complicated, right? And then you have to apply it, right? But of course I will write this with wrong color. Right. So if net torque, which we wrote just a second, net external torque equals 0, because again, internal torques are not capable of changing total linear momentum. They're capable only in redistributing angular momentum within the system. Then angular momentum is conserved. Then I will just write L initial must be equal to the total angular momentum final, right? For example, before collision, after collision, when rotational motion is involved. Again, we will look at examples. Right. Okay, we're getting closer to the end of the exam review. I mean, to a review of the most important points, right? So pretty much about each of these points, there will be some questions on the exam, right? And in my opinion, these are the most important in chapter 12. Then, let's look at how can we calculate gravitational potential energy of a rigid object. For example, I have this cup, and I realized that I need to show. How can we find potential energy of this cup, let's say, for example, relative to this reference level? Let's say here gravitational potential energy equals 0. So what do we have to do? You find the center of mass, all right? Then imagine, of course, imagine squeezing the whole object at the point mass, which is positioned at the center of mass, right? And then just calculate the potential energy of that point mass relative to this point. It will be mg times this distance, right? Okay, let me write that down. So it's one of these amazing features of the center of mass. This center of mass, in a sense, center of mass, simplifies calculations of many things, right? You will see it throughout your classes. So now, let me write this. I will put a small bullet. Gravitational potential energy of a rigid object. Rigid object. So let's say you have some arbitrary shape, rigid object of an arbitrary shape of the total mass m. And let's say you picked, you remember every time when you deal with gravitational potential energy, you need to show where is your reference level, where is your potential energy equals to 0, gravitational potential energy. So let's say this is my U equals 0, reference level. So and then you just find the center of mass point, Cm, right? Center of mass. If it's a rigid object, most of the time, not most of the time, every time, our objects are going to be symmetrical. Spheres, disks, squares, triangles, right? Rods. In that case, it's very simple to find the center of mass, just at the centers, right? And the center of symmetry. And so that's what you need. So this is YCM. As a result, U potential energy will be mg y of the center of mass. Okay, let me frame it, because again, it can be shown, we did not show it, right? Because this is an introductory level physics. Good, so now the last piece, and then we will start looking at problems actually. The last subject which we discussed, stability of system, static equilibrium. Right? How to guarantee that your system, like this camera, will stay without crashing down or this way, or prevent any rotational motion. Okay, static equilibrium. Static equilibrium. Okay, so I will just write down. So we need to satisfy 3 conditions. So to avoid having any translational motion in the x direction, you have to balance all forces in the x direction. It's just basically a translational Newton's second law when acceleration equals 0. Right? In this case, this camera is not going to move in the horizontal direction because all the forces are balanced. Right? So then, second, if you want to avoid having any translational motion in the y direction from the unknown. You have to balance all the forces in the y direction. Again, all the forces in this case, normal force balances force of gravity as a result camera stays on this floor without getting through the floor and getting into the basement. Then, the third condition. In order to avoid having any rotational motion, we need to balance torques. All torques. Because torques producing rotational motion. If you want to avoid having any rotational motion, of course you need to balance them all out. And the beauty is, it simplifies tremendously calculations, right? So if these two conditions are satisfied, then it doesn't matter which axis of rotation you pick. If you balance torques around any axis of rotation, then you know that torque around any other axis of rotation will be zero. So you would never be having any rotational motion around any axis of rotation. So then we have a freedom to choose any axis of rotation. Again, it is only true when you satisfy this, but every time in the problems we satisfy that and then. So let me write. So this is the choice of axis is arbitrary. Let me write. You can use any axis of rotation. And of course, whenever you have this freedom, of course, you can pick the best axis of rotation to simplify your calculations. Okay, that's it, right? Let me frame, of course, these conditions. And now we will start looking at examples. Okay, cool. Okay, let's practice a little bit a right-hand rule first. How to find direction of the cross product. Again, in Physics 2, in the second half of the semester, I will bug you until you will start applying it properly. Because then you wouldn't be able to pass the final exam without knowing how to apply right-hand rule. All right. So first example. Let's say, again, what we want to get. We want to calculate the cross product between A and B, so the cross product is C. So let's say we have A this way, B that way. So what's the direction of the cross product? First of all, you need to remember that C must be, by definition, must be perpendicular to both of these vectors. So immediately you have only two options, either out or in the board. Right? So now apply right-hand rule. A line along the first vector A, your hand, your arm, then orient it so that you can bend towards the second vector B. Right? And your outstretched thumb gives you direction out. Or, as I keep telling you, how my professors taught me, they would usually suggest to grab this vector B, second in the product. Position it over here at the end of the first, so you'll have like this flow. And just curl your fingers in that direction. And your outstretched thumb gives you direction. That's what mentally, all the time I do it. I just move this vector that way. And direction is out. So in this case, it will be out. Out is a dot. Wait, it's not C, it's C. So direction of C. Now let me turn the system in all possible directions. So let's say A is in A vector, then B is up. So what will be the direction of the cross product? First, again, you need to restrict yourselves to two possible directions. C must be perpendicular to both of them. A is in, B is up, so they form this plane. So C vector must be perpendicular to this plane. You see? This plane. So it should be either this way into the plane, or this way or that way. So there are only two options. So now quickly apply right-hand rule. All right. So what we have? A first in, B. So we have this system, right? A and B up, right? So I will just curl my fingers in this direction, and it gives me a direction that way. Or first a line along A vector, and then turn your fingers towards the second vector, and you will get C vector to the right. So that is my C vector. Okay, in this case, of course, you need to turn on your imagination, right? Make sense? Okay, now another example. Let me turn again everything. A this way, B this way. Yeah. So A that way, B is towards you. Again, so A that way, B this way, so you have this system, right? So align your hand along the first vector A, right? Then orient it so that you can naturally bend your fingers towards the second vector, right? Of course, I know Thai people can naturally bend their fingers really, really, right? But those are exceptions, right? In the traditional Thai dance. So you need to position your hand this way, so you can curl your fingers towards the second vector B, and your outstretched thumb gives you direction of the C product, or a C vector, cross product. So then this will be vectors, okay, something fall down, C. Okay, and the last example, let me turn it this way. A is out, and B is at this strange angle. So, three-dimensional. So this is vector A out, B is, right? So this we have system. We have this system, right? Yes. Again, so first, restrict yourself to two possible directions. So C vector must be perpendicular to both of them. So these two vectors form this plane at this angle, right? So it must be perpendicular to this plane. So it means that C can be either this way or that way. My plane is not very stabilized. So now right-hand rule. First, align along first vector A. A is towards you, right? Then B is that way, so I need to orient my hand this way, right? Curl my fingers. Vector C is this way. So vector C. Again, in physics 2, when we get to magnetism, you will never be able to solve any problems without this right-hand rule. Most of the problems. Here in physics 1, I'm still a little bit. Yeah. Say it again.
Is it the same right-hand?
Of course, this is tool which was created by mathematicians for everyone, right? Even if you're a housewife, you can still use it, right? Of course, it's useless, right? But you can use it. Right? Of course, we use here two right-hand rules. At least I labeled them, right? So first one, it's how to calculate cross product, and second, how to find the direction of omega, angular velocity, right? And again, in physics 2, again, we're going to use exactly the same two right-hand rules to calculate the cross product, and then to find the direction, for example, of a magnetic field created by a straight wire, infinitely long straight wire, right? Okay, so now let's practice moment of inertia. Okay, I will erase this now. So moment of inertia. So let me give you this system. A rod, of course, uniform rod of length L, right? Length L, I think, yeah. length L. Then, here is the center of mass, right? This is the center. Okay, let me emphasize that this is center of mass. Center of mass for symmetrical object is, of course, is at the center of symmetry. Then we have two short massless rods. This is massless. Massless. Right? And at the end of this rod, there is a point mass M. Then, let me create exactly the same situation on the other side. Exactly the same length, exactly the same mass M. Again, this is massless also. This is massless. Okay, massless, it means much lighter than the mass of the rest of the system. So we need to find moment of inertia. If I ask you, find the moment of inertia, what should be your response immediately? If you tell me, calculate moment of inertia, what should be your response? Huh? Yeah, you're trying to apply mr squared, right? No, but what should be your response if I ask what is the moment of inertia? Guys from my sections, I bugged you about this moment. Right? Moment of inertia depends on what? Axis of rotation. If you don't know around which axis you're going to spin your system, right? The question is useless. Actually incomplete, just basically, right? So moment of inertia, what is this R? When you said it's mr squared, what is this R? It's a distance from the axis of rotation to the point where the mass is. So if somebody asks you to calculate either moment of inertia, or torque, or angular momentum, just the question by itself, find this, is incomplete. You have to also every time specify relative to which axis of rotation. Where is your origin? Usually we position origin at the axis of rotation, right? Because all these rotational quantities, they depend on the axis of rotation. You see every time, R is here, R is there, R is here, right? So now let me give you a complete question. Axis of rotation goes through this end of this rod. Now the question will be complete, and now my question will be legitimate. So that is my axis of rotation, and let's say omega, which small one, omega. That is my axis of rotation. Axis of rotation. Okay, so now, you know what, before we start calculating, let's refresh. What will be the direction of omega as a vector? What's the direction of omega in this case? Right-hand rule number 2. Counterclockwise, yes, that's a nice trick which is used in introductory level classes, right? But by the end of this class, right, we started also treating it as a vector, right? So it's a pseudo vector because direction is according to the convention. Convention is this. So if you curl your fingers in the direction of rotation, your outstretched thumb gives you a direction of this omega, right? So for example, that door, when you get out, what's the direction of angular velocity? That side of the door. You see, door opens that way, here at the hinge. Right, so curl your fingers in the direction of rotation, and your outstretched thumb gives you direction of omega. So for that side, for the left side of that door, omega is up. For this side of the door, now that door opens outside, so now you curl your fingers this way, and your outstretched thumb gives you direction of angular velocity. For this right side of the door, omega will be down. Right. For example, I have this, right? So let's say I'm turning it this way, right, around this axis of rotation. So curl your fingers this way, your outstretched thumb gives you angular velocity, direction of this vector. Okay. So in this case, omega is up. So that is my omega pseudo vector. course, yeah, sometimes we use it as counterclockwise, or in a higher level classes, because you will treat it as a vector. Okay, so now let's calculate moment of inertia actually. Moment of inertia is additive thing. If you have like 4 pieces, for example, how to find total moment of inertia? Just calculate moment of inertia of this, and then add them all up. Right? So it's simple. So now let's do the same. So right, I total. So it will be moment of inertia of one mass plus moment of inertia of the second mass plus moment of inertia of rod, and the mass of the rod is given, m capital. I forgot to give you this, right? Plus moment of inertia of that rod. So, can you tell me immediately what will be the moment of inertia of one mass, this mass, for example? It's strictly speaking mr squared, right? What is r in this case? R, it's the distance from the axis of rotation to where the point is. And point is this distance, which is L over 2. You see, this is L over 2. So let me use different colors so that it's part of this picture. So that is R equals L over 2. And exactly the same story over here. R equals L over 2, right? For these two masses. So contribution to the total moment of inertia will be exactly the same for both of these masses, although one is positioned over here, second position over there, but relative to the axis of rotation, they are in exactly the same, under the same conditions. So now let me continue this. This will be ml over 2 to the power of 2. Don't forget it's square. Again, these formulas are given in the formula sheet. You can easily find them. Then contribution from this mass will be exactly the same, ml over 2 squared. Again, guys, if something not clear, right, or you're getting lost somewhere, tell me immediately, right? I think I'm talking about things which shouldn't cause any significant troubles. Then how can we find this? Of course, I will give you in the problem on the exam, right, a moment of inertia, because this is a rigid object, right? You're not at that level where you can calculate moment of inertia over a rigid object. You will have to go through calculus 3. So plus, it's, I even don't remember. I have to look 1 over 3. Of course I can calculate, but I don't remember at the top of my head. It's a moment of inertia over uniform rod when the axis of rotation goes through one of its ends. It's from table 12.2. Okay, let me emphasize that this is table 12.2. But on the exam, of course, I will give you formulas like this. Because memorizing these formulas is just a stupid thing. Okay, so all these numbers are given, so you can calculate it, right? Number if it's needed. Actually, I can simplify it. It will be L squared, m small over 2 plus m capital over 3. Okay. So every time in this rotational dynamics, we can have either point masses and rigid objects. Rigid objects. Any questions? No? Okay. Now let's calculate now angular momentum. Angular momentum. Let me separate this. No, wait. Separate this. Wait. This way. So now angular momentum. Let's calculate angular momentum. This system. Okay, I will introduce first coordinate system and then we'll draw the picture. So let's say this is my x-axis. Just to confuse you a little bit, so I align x-axis in the vertical direction, so it's not a big deal. So then y-axis this way. And in order to have a right-handed system, x cross y should give me z, so z must be into the board. Z is into the board. So this will give me a right-handed system. Never use left-handed system, because you will start getting minuses in unexpected places. Now, 2 points of line, I don't know, 2 bullets or whatever. So first one, this is second, this is first one. Let me draw it here. So first mass, m1 equals 1 kilogram. And it's flying this way. With velocity, v1 equals to 3 meters per second. First object. And again, you remember what's the feeling, what's the idea of angular momentum? It's a quantity which allows us to describe its ability to create rotational motion. If, for example, this mass will interact with, for example, some disk over here position, right? If it interacts with that disk, it will be able to create rotational motion because it has a certain amount of angular momentum. Okay, so now the second point, let's say this point, point M2, which is 2 kilogram, is flying this way in the opposite direction with velocity v2, which is 2 meters per second. So this is the line of motion of the first mass, and this is a line of motion of the second mass. So it's flying along this line. They are flying along these lines. Then what else is given? We know that this distance is L2 equals 1 meter, and this distance L1 equals to 2 meters. Right? Okay, so now I think I gave everything in order to calculate what is the total angular momentum of this system. Right? Again, it's ability of the system to create some rotational motion. Again, I can imagine, let's say we have here some disk, right, and these 2 bullets are colliding with this disk. Of course, they will create some rotational motion, and that quantity, angular momentum, is capable of describing it. Right? So, we have 2 expressions to calculate angular momentum: point mass and rigid object. Definitely, those are not rigid objects. So we have to use formulas by definition. Again, it will be given on the formula sheet, right? So L equals R cross P for point mass, for a point mass. And again, angular momentum is an additive thing. If you have 2 objects, just calculate angular momentum of one and the second. But angular momentum is also a vector. So you have to keep track of the directions. And we're going to do that. And of course, we will need the right-hand rule. That's why I started with the right-hand rule. So let me write in general. So L total equals L1 plus L2. Step by step. Making it more and more complicated. Right? So we just need to apply this formula twice for this case and for that case. So I can calculate, I can write R1 cross P1 plus R2 cross P2. Just by definition, apply definition twice. Nothing fancy. So now, where is R in this definition? It's a distance from the origin, or possible axis of rotation if you have some object from the origin to where the mass is right now. So this will be my R1, right? And this will be my R2. So what can we use? So first, let me probably write magnitudes, absolute values of these L1 and L2. Can we use any of these formulas? These are formulas to calculate absolute value, right? Of a cross product. Of course, they are written for torques, but I wrote over here, it can be used to calculate L as well, right? So we can use, for example, R perpendicular times, instead of F, of course, we're going to have P. Okay. So we can use exactly those guys. Right? So let me write R perpendicular for first object times linear momentum, P1. And now direction. What will be the direction of angular momentum L1? Right-hand rule. Cross product. Into the board. I have no idea. I need to apply right-hand rule, right? In the board. Okay, let's see. First, I align, because it's an R cross P, so first I align my hand along the first vector in the cross product, R. Then I need to orient it in such a way so I can bend naturally towards the second vector P. So as a result, my thumb gives me into the board. So there are two options, either on the out or in. You see it? Okay, so now in is plus z direction. Cross it's in. So let me write plus k hat. It doesn't mean that we're adding, it just we're multiplying by the positive vector. Because I put a brackets around. And now let's do the same for the second. Of course it will be R perpendicular for the second object, P2. And what will be the direction of the second angular momentum? What? Out? Out? Yeah, out. So R that way. Right, and I need to position this way so that I curl my finger. I can curl my fingers, turn my fingers towards the second vector, which is P along V. And so it will be out. Out is minus Z. Bless you. So minus K hat. So you see, they are in opposite directions in this case. Next problem we will have in the same direction. Okay, so and now let's write what is R perpendicular for the first object. What's the value of R perpendicular for the first object? Louder. Okay, what is R perpendicular? This is the first object, line of motion, and this is the distance, the shortest distance between the origin or axis of rotation and this line of motion. So this distance, right? Which is given L1. Of course, you can do it mathematically and from these definitions. You remember, like in the lecture, I calculated moment of inertia of a ball dropped from my hand. You remember I did this example. And what we ended up with, just linear momentum of the ball times this distance. Here I position the origin, right? So this distance is the shortest distance between the line of motion and the origin, right? So that's what we have here. Here's my shoulder, here's the ball moving, okay, moving this way. So we need to use just L1. So linear momentum times L1, that will be the magnitude of the angular momentum. So it will be, okay, I will continue here right underneath. So it will be L1 times M1 V1 in the plus Z direction. Linear momentum is MV. Right? So that's what I wrote. Linear momentum is MV. And the same story for the second object. What is the shortest distance between the line of motion, here's the line of motion, and the origin axis of rotation if we want to create rotational motion around this axis, around this point. So again, it's this distance, which is L2. Exactly the same like what we did to calculate torques. For the torque, we use this line of force. For the angular momentum, line of motion. And I proved it in your lecture, in our lecture. So now plus L2 m2 v2 and in the minus a direction. So now you can plug numbers because everything is given, all the velocities, all the masses, distances, everything is given. So you can plug it and you will get eventually, you will get 2, of course, in the z direction, because this positive value will be larger. You can plug numbers. 2 in the k hat, and units. There are no special units for the angular momentum. Just whatever you see in the formula. So it's a kilogram times meters divided by second. Kilograms meters to the power of 2 divided by second. Kilograms times meters to the power of 2 divided by seconds. So that is preparation for the next problem, where we're going to use conservation of angular momentum, and we're going to have 2 objects, point mass and rigid object. So now let me erase this. Okay, this will be a little bit longer problem. The story is this. You have a rod. I think I have a rod over here. Okay, of course it lies horizontally on a frictionless surface, on the icy surface, right? And let's say we have axis over here, like an axle, which goes through the center. And then you shoot a bullet through the midpoint between the end, this end, and the center of mass. Right? And let's say bullet doesn't get stuck inside. It just flies through. So bullet before flies this way. After collision, it continues flying, of course, with a smaller velocity. Right? So we need to calculate the angular velocity of this rod after this interaction. Of course, the rod will start spinning, so we need to calculate angular velocity. Or you can look at this problem like a strange way of opening the door, shooting the bullet through somewhere in the middle, through the midpoint of the door. It's a similar, math will be very similar. Okay, I will erase this because now I need room. Right. So now I will label this conservation of angular momentum, because that's the most important idea of this problem, conservation of angular momentum. Conservation of angular momentum. Okay, I will draw the picture. So first, I have a rod, longer. Total length L. Total length L. Axle goes through the center of mass. So here is axis of rotation. So actually there is an axle. Of course, no friction. Here is, here comes a bullet, right? Mass M, which moves with velocity d1. So this is initial situation, right? So let me write, it's the initial situation, and I will label it as situation 1. Right. Situation 1. So the bullet flies through the center, right? So it means that this distance is, what will be this distance? In terms of L. L over 4. L over 4, of course. L over 4, because it goes through the center of L over 2, right? So this distance, of course, will be L over 4. So it's initial situation and now final situation. Okay, that will be situation 2. So now, right after the impact, the same rod, this axis of rotation. Let me align these lines. Right. So now the bullet will make a hole. We will neglect the change in mass of the rod. It will be minuscule. Right. So now the bullet, after this impact, will be flying this way with velocity v2. Of course, v2 will be smaller than v1. So initial, and that is our final situation after the impact. Okay, now let me give you some numbers. Right. Everything now. Yeah, and of course, this rod now will be spinning. Of course, this rod will be spinning now with some angular velocity which needs to be found. Okay, now let me give you numbers, of course. Right. So, length of the rod is 1 meter. Then mass of this rod is, well, actually it's quite light, 20.27 kilograms. Then mass of the bullet, m small, 3 grams. Of course, pay attention to the units, right? Sometimes I can see that grams are given and grams are used in the formulas instead of kilograms. Right? Just a silly mistake, right? Just lack of attention, right? Okay, then velocities. V1 equals 250 meters per second, right? And V2 after the impact is 140 meters per second. So you see velocities are smaller as it should be after collision. Of course, it will lose some velocity. Then, what else we would need? As I told you, whenever you have a rigid object, rotation of a rigid object, right? We need the moment of inertia of a rigid object. And I told you, of course, I will give you that formula. So in this case, a moment of inertia over rod, over stick, when the axis of rotation goes to the center of mass, I of a, which where I just wrote, stick, I think I used rod. Whatever. Rod equals 1 over 12 ml squared. L, the total length of the rod. The total length of the rod. Okay, so that's it. Right? So what we need to find? We need to find omega. Okay, let me label it as omega 2 because it's related to the situation 2. Let me label it omega 2. Makes sense. Let me ask you first, start asking this question. We're going to use law of conservation. But let me, how many laws of conservation do we know so far in this class? 3. First one, conservation of mechanical energy. Is mechanical energy conserved here? Why not? Bullet damages that rod, that piece of wood. Damaging wood, it means that lots of mechanical energy will be lost making that damage. All right. Of course, the bullet will be warmer, right? The block will be damaged, and temperature of the block will, okay, not block, the rod, right? The temperature will go up. So that all happens because of the loss in mechanical energy. So mechanical energy is not conserved. Then, conservation of linear momentum. We have rotational motion. Linear momentum is useless for rotational motion, right? It's not applicable, right? It will be just silly to use the conservation of linear momentum here because we have rotation of the rod. Yeah, you can introduce linear momentum for the bullet, but the system consists of a rod and a bullet. You cannot calculate linear momentum of the rod which is spinning. So we have only angular momentum to do that. So of course we left only with angular momentum, conservation of angular momentum. And as I told you on the exam, of course I will tell you somewhere in the problem, use conservation of angular momentum. Right? because justification is more complicated. Of course, there is only one force which can ruin conservation of angular momentum. It's a friction at the axle. That's the only force which can ruin conservation of angular momentum. We will assume that that friction is zero. Right. Okay, so I will just write, we will use conservation of angular momentum. Actually, I already wrote, right? And so let's use conservation of angular momentum. So we just need to compare angular momentum before and after. So it will be L1 equals to L2. I did not write it down as a vector. Let's quickly, can you tell me what will be a direction of angular momentum of this bullet? I just erased the problem. We looked at two we looked at the angular momentum of two particles. So what will be the direction of angular momentum of this bullet before collision? In the board or out of the board? Right-hand rule, and this is R, right? This is R. R cross P into the board. Now, in this case, this is this is R, right? Again, R cross P into the board. So angular momentum of this and angular momentum both into the board. Then, what will be the angular momentum of this rod when it starts spinning? How can we find angular velocity? And angular velocity, you see what? Angular momentum of the rod. It's a moment of inertia times angular momentum equals moment of inertia times angular velocity. What's the direction of angular velocity for the rod? What? Into the board. It will be spinning this way. So curl your fingers in the direction of rotation, and your outstretched thumb gives you L. So you see all these L's are in the same direction, right? So we don't have to subtract, we just add them all up, right? So we don't have to take care of the directions. So that's why I dropped signs of vectors. Okay, so now let me write explicitly. The system consists of two objects. Let me follow my notes which way I labeled them. Yeah, this is of course total angular momentum. So it's a total, here let me write L. L is the total angular momentum. L is total angular momentum. Because system consists of two objects. A bullet and this rod or stick. So I can write L1 of the bullet, BUL, upper script, initial, situation 1, then plus L1 of that rod or stick. Just I'm writing down everything which is possible. Then angular momentum of the bullet after the collision, again BUL, bullet stands for bullet. And angular momentum of the rod. Angular momentum of the rod after the impact. We have a point mass, bullet, and we have a rigid object. So we have to use this formula and this formula at the same time, right? Right? So what is this L1? It's a rigid object. It's a I times this I rod. Let me write I rod times omega 1. So what is this? 0, because the initial condition, according to our initial conditions, the rod was at rest before the impact. At rest, angular velocity is 0. So let me show that this is 0. As a result, this can be dumped. So before collision, the whole angular momentum is in the bullet. Rod is not contributing anything to the total angular momentum. Now, after the impact, angular momentum of the bullet or of the rod, it will be again the same. It's a rigid object. It should be black. Right. So again, it's a moment of inertia of a rod times now omega 2, which we need to find. Dealing with angular momentum of a rigid object easier, significantly easier. Now let's find the depth. Yeah, and this was depth. So let me write it underneath. L1 of a bullet. And you see it's absolute, it's a magnitude, absolute value. Of course, strictly speaking, it's R P1 and times what? Sine of angle, right? You see, it's a cross product R cross P. It will be magnitude of R, magnitude of P, or sine of angle. It's like over here, right? We can use this to calculate angular momentum. So we can use either this, or we can use this trick, R perpendicular times F, or F perpendicular times R. Which trick will be easiest? Can you look at the picture and tell me what is, for example, for this case, what is R perpendicular? By just looking at the picture immediately. What? Oh, L over 2, oh no, L over 4. Right? This is the line of motion. And R perpendicular, it's a distance, the shortest distance, the perpendicular distance between the axis of rotation, and that's where I position my origin, and this line of motion. We're talking about this distance, which is L over 4. So that's why these tricks was introduced, because sometimes we just look at the picture and you can see immediately that. So you don't have to look at this. What is the angle? What is R? It just simplifies calculations a little bit. Right? So of course I can do it like this. Angle is 90 degrees. This is the angle, right? No. Don't listen to me. It's BS. I get carried away. So let's just use R perpendicular, second way. R perpendicular times P1. Right. Again, if you want to see how it can be shown, again, when I was dropping the ball and calculated angular momentum of the ball, I did that. So, and R perpendicular, like you just told me, it's L over 4. It's this distance, right? Okay, let me write that this is R perpendicular for the first case. R perpendicular for the first case, which is L over 4. Let me emphasize it's the first case over here. Also, you see upper script 1. And V1, linear momentum, mass times velocity. MV1. So now let's do exactly the same for L2. L2 of the bullet equals, again, it will be RP2 sine of angle, or we can use the same trick, R perpendicular for the second case times P sub 2. I think it's time for me to change the marker. It's getting drier. It's also not good. Oh, this isn't good. Right? What is R perpendicular now for the second case? It's exactly the same, right? Because the line of motion the same, the axis of rotation at the same place, right? So of course it will be also, let me continue, R perpendicular for the second case. So it will be L over 4 times MV2. Right. Okay, so we're almost done. So now let's just put all these ingredients into the common place in that equation and finish. So now let's just put it over there and finalize our result. Separate it this way, and I will continue this. L1 bullet, where is it here? L over 4 MV1. It's the first term. Second term is 0. The first term on the right-hand side, L2, it's this, equals L over 4 MV2. And contribution from the rod. Now our rod is spinning, contributing something. I rod times omega 2. So now we wrote down conservation of angular momentum explicitly for this case. Only one unknown is here, right? Omega 2, that's it. Given. I wrote, where is it? Here. Mass is given, length is given. Everything is given except for omega 2. So that's the only quantity which is unknown, and that's what we need to find, so it's fine eventually. So omega 2 would be equal. This goes to this side, and I will factor out L over 4 and mass, so it will be V1 minus V2. So this term just goes to this side with minus L over 4m common factor, so we can factor it out. So we'll have V1 minus V2. Right? And then I will take this I rod, because now on this side I will have only this factor. This term, I rod, goes downstairs in the denominator. So it's an I rod. Just simple algebra. At this point you should be able to. Okay, so now let me plug the expression for I rod. L m V1 minus V2. Factor of 4 I will bring downstairs. And moment of inertia 1 over 12 m capital L squared. 1 L can be cancelled. You can easily do this. And if you plug numbers, I'm not going to do this. Yeah, don't forget that this is mass is 3 times 10 to the power of minus 3 kilograms. Because it's quite often I see students would forget at the end when the result is very close. You get excited, right, and you can forget about the small things. I've done similar things sometimes. That's why usually, even in the statement of the problem, I will immediately change all these units so that I wouldn't make at the very end a silly mistake. I don't trust myself. All right, so if you calculate all this, you will get 3.66 radians per second. So units of angular velocity. Yeah, probably I should have said it's a top view. Let's say it's a top view on the situation. Now, can you tell me what's the direction of omega? So we calculated the magnitude of omega, angular velocity, but what is the direction of omega? Yeah, absolutely. It's a clockwise, but in terms of as a vector, if we looked at omega as a vector, pseudo vector, you remember the right-hand rule number 2. So just curl your fingers in the direction of rotation, and your outstretched thumb gives you direction of omega as a vector. It will be into the board, right? Into the board. Like the same like what we were talking about when we were talking about the door, right? Rotation. If it's a top view. Right. Now, problem is done, right? So the problem was about this. Now, if I ask you, can you calculate kinetic energy over a rod? Can you do it? The formula for the kinetic energy, rotational kinetic energy is over here, right? 1 over 2 moment of inertia times angular velocity, square of angular velocity, right? So now it's just a question of just crunching numbers and getting it done, right? So let me write also. We can also calculate K rotation, which is 1 over 2 I rod times square of the angular velocity, right? So let me just, I'm not going to plug numbers. Everything is given, moment of inertia is given, right? Angular velocity we found. You will get 0.15 joules. It's just a question of just using the right expression. So we've been here 1.5 hours. We still have 1 hour. I hope there is no one booked this room after us. Okay, the next problem I will probably skip for now. Let's just discuss. let's say you have a turntable spinning, right? Spinning turntable. And you will just drop a rod on the turntable. You know masses, you know the length and diameters, right? So, and of course, after sort of collision, right, the rod stuck, right, on the disk, and they all start spinning, of course, with a smaller angular velocity. We need to find the final angular velocity. It's a, again, problem on conservation of angular momentum. Conservation of angular momentum. Of course, I will tell you that on the problem. Here in this problem, it will be easier. You don't have point masses in this example, because we have what? We have turntable, rigid object. Moment of inertia will be given. Rod, rigid object, moment of inertia is this, right? So you just calculate angular momentum before of the turntable, which is I omega trivial. And after, now it will be one rigid object. You just calculate moment of inertia over rod plus moment of inertia of the disk, turntable, and multiply by the unknown velocity. Again, you will just have one equation like this with I omega on one side and I omega on the other side. Of course, I will send you my notes. You can look carefully at that example. If we have time, I will look at the end. Now I will just skip it for now because we have big problem. Right. Any questions about this? Right. Okay. I only wanted to mention about this, right? So before the collision, the whole angular momentum is in the bullet. This contributes nothing. After the collision, the whole angular momentum is in the bullet and in the rod. So what happened during the collision? Bullet shared angular momentum with a rod, with the rod, right? And those internal forces over here during the impact, and of course internal torques, actually, that's what we would have to discuss if you want to analyze that. Those internal torques during the impact, they allowed us to share angular momentum. First it was in the bullet, now it's everywhere. So bullet shared angular momentum through those internal torques. Internal torques cannot change the total angular momentum. It's still the same, let's say 5 before, 5 after. But those internal torques allows us to share angular momentum between members of the system. As I told you in my classes, right, it's like a government, right? It doesn't make money, it just collects from companies, right, and then share it according to whatever standards, right? So the same internal torques, they just share it within the system, right? They're not capable of changing. Now, okay, no questions? Again, if something not clear, tell me. Okay, let me check my camera if it's still alive. Yeah, it's still recording. Okay, good. Now, the next one. Atwood machine, but now the pulley is not massless. You remember we solved in the previous, I think, exam review session. We looked at Atwood machine. But back then, I told you, okay, let's assume that pulley is massless. And then analysis was much simpler. Now we're not going to make that assumption. We're going to assume that pulley has mass, has a radius, and we will have to describe the system. I will tell you what we have to find. I will start erasing this. So now, let me label it pulley and masses. Next problem. Pulley plus 2 masses. Okay, I will start with a picture, of course. Let's see, this is my pulley. Of course, I exaggerate, make it bigger. Here is one mass. Here, so there is a rope which goes over this pulley. Here is the first mass. It's M1 and M2. No, on this side it's M2. On this side, there will be the second end of this cord, and there will be second mass. No, actually, first one, M1. Then this is the axis of rotation. We will have rotational motion of a rigid object. What do we need for that? Moment of inertia, I. Moment of inertia. So let me. Actually, it's not a disk. It's a hoop. It's a hoop. Okay, let me emphasize. So this is a hoop, right? Pulley. So it's not disk. Okay. It's not a big deal. It can be a hoop. And the moment of inertia of a hoop, I of a hoop, is mr squared. Radius is given because at the end it will disappear. But of course, in order to get through the problem, we will have to introduce radius, right? Otherwise, we wouldn't be able to get through algebra, physics and algebra. Yeah, that's it. What is given. So what do we need to find? We will need to find acceleration. Acceleration, of course, will be the same for this mass and that mass, right? Acceleration constraint. Okay, let me erase this. And so what do we need to find? Acceleration. I don't put any subscripts because acceleration will be exactly the same for both of these masses. So let's start analyzing first. System consists of three objects, two masses and a... It happened in the past with one of my advisors. I was doing my research in the lab, right? And on the weekend we were playing tennis with my friends, and I fell down, and these two fingers hurt, right? So I couldn't use them, right? So I came to my advisor and I told him, we need just one thing, and of course I used the next finger. He started laughing to me, you don't use it. Of course I knew, but I was surprised why I used that finger, just because these two fingers, I was in pain. I didn't think straight. So sometimes it still happens, right? But I hope no one get offended, right? Yeah, so three objects. I'm not showing anything, right? And yeah, how many types of motions we're going to have here? Of course, two, right? All right, so we have translational motion of M1 and M2, and pure rotational motion of the pulley, right? So I will use, so for M1, pure translational motion. And of course, which universal law is capable of describing any possible translational motion? Of course, we all know that, because I keep telling you about this. That's a translational Newton's second law, right? Newton's second law. Net force equals mass times acceleration. So net force equals mass 1 times acceleration. So universal law will have to apply for this mass, for mass m1, to describe pure translational motion. Then for m2, exactly the same story, pure translational motion. Pure translational, again, net force acting on the second object will be equal mass 2 times acceleration. Universal law. So we'll have to apply universal laws 3 times. And the last one, now for the pulley, M capital pulley. Now, of course, it's a pure pure rotational motion, right? Pure rotational motion. Pure, now, rotational motion. And again, universal law, which describes any rotational motion at any point of the universe at any moment of time. Rotational Newton's second law. I'm not going to use this general form because even this works. I think this will be easier to use, right? So let's just use this form of rotational Newton's second law. Nothing, just fundamental stuff. Again, I told you, right? So these things, Newton's second law, we cannot derive, we cannot prove them, we just believe them. Believe in them and use them because they describe everything which we can see. I told you at the beginning of the semester, we are in the cult, we're believing in these Newton's laws. Right, so net torque equals moment of inertia times alpha. It's everywhere in the physics. There are some axioms which no one can prove, no one can derive. We just accept them because they help to describe what we see around us. And then use logic to explain more complicated systems. So now, after that, so now we understand what we have to apply. So whenever we have to apply Newton's second law, what should be the next step? Free body diagram, right? Free body diagram. Everything must be in front of us. You don't have to invent anything new, right? So let's start. M1. Okay, I'm not asking you because these forces are ubiquitous and you've been using them so many times. All right, so M1G, downward, of course, right? Then tension from the cord. Cord can only pull, it can never push. So it means that force acts along the cord, away from the objects. Still, I sometimes see this force in the opposite direction. This force tension cannot push, it can only pull. So that force must be drawn from the mass along the cord. Now, this is, I will label it as T1. Now, I'm still going to assume that this cord is massless. Massless. If the cord is massless, what can we say? What's the conclusion? Tension is exactly the same at any point of the cord, up to this point. After this point, this cord will be involved in turning this pulley, and the pulley is not massless. So it means that on the other side of the pulley, tension will be different. Before, when the pulley was massless, tension over here and tension over there was exactly the same. Now, since we have to apply some efforts to turn the pulley, because now it's not massless, it requires some efforts to turn. So of course, it will be done because of the difference between these two forces. So this force must be different than force of tension in this part of the cord. Okay, so now here T1, and of course the same force will be acting on the pulley, but of course in the opposite direction. But the absolute value is exactly the same because the cord is still massless. Cord is massless, pulley is not. Now, this side, exactly the same. Two forces, right? Three forces, right? So here I will have M2G, force of gravity. Yes, sorry, it's getting below the table, right? I cannot push this table out. And this will be, now I will label T2 because it's on that second side of the system around mass G. And again, this cord is still massless, so over here I will have T sub 2. But again, tension on this side and tension on that side of the pulley must be the same in general situation. What? Of course, there are also gravity acting on the pulley, which will be balanced by the normal force from the axle. So we can forget about those forces. They're not going to do anything. They just balance each other out. I drew them once in our lecture, but I'm not going to do that anymore. You should be able to understand that those forces are not going to do anything. So now, next step. In order to complete free body diagram, what do we have to do? We have to introduce coordinate system, and we have to show positive direction for a torque. In this case, we're not going to use right-hand rule to calculate torque. We're just going to use that freshman level convention, right, for positive direction of the torque. No, you know what? Yes, this will be my plus tau CCW direction. But before I can introduce coordinate system for these two masses, I will have to, okay, can you tell me what will be the direction of acceleration? Counterclockwise, because that mass is heavier than this mass. Basically, we can see that. But if, for example, masses were not given, let's assume if masses were not given, right? In that case, you would have to make an assumption. about the direction. Like what we did when we were discussing this problem, I think in the previous exam review session. Right. So usually I would assume counterclockwise direction because that is a positive direction for everything, right? And then if you, after calculations, your acceleration happened to be negative, okay, we can make a small adjustment. So my original assumption was wrong, blah, blah, right? So, but in this case, we know that acceleration will be that way. So now let me emphasize that acceleration is downward, A here, and A there. Why I started with acceleration before I introduced coordinate system? Because I don't want to forget that my acceleration negative, for example, right? If I pick the wrong, not the wrong direction, different direction for the axis, my accelerations can be negative. I just want to have my accelerations to be positive. So I will pick my y-axis for this mass upward, then acceleration will be positive. Right? And chances that I'm going to forget about the minus over here was 0. And for this mass, I will take y-axis downward. Right? Again, just to reduce chances of making a mistake. So now, as a result, after all this, I can say this is my y-axis for mass m2. I can use that. I can use different coordinate system for different masses. They will be linked through the acceleration anyway, through the absolute value of an acceleration. And for this mass, I will pick this y-axis to write down Newton's second law. Okay, so now I can say free body diagram is complete. Everything is in front of my eyes, and now it's just a question of transforming picture into the equations. Okay, now let me continue this line. I mean this for M1. So M1 forces, M1G positive? Positive, because it's in the positive y direction. Attention negative, because it points upward, negative y direction. So it will be M1G minus T1 equals mass 1. And acceleration is positive because it is along positive y direction. That's why I picked y direction downward. So times A. Okay, so that's my equation number 1. Now we just start collecting all possible equations from our universal laws. Now the second one. Now M2G negative. Right? It negative. Y-axis upward for this object, and T2 now is positive. So now second equation will be T sub 2 minus M2G equals mass, second mass times acceleration. Again, acceleration is positive. Because again, I told you already several times, you guys have a strong habit of keeping track of directions of forces. But acceleration, sometimes we can forget. Even sometimes I can forget about this. You just develop a strong habit, and then as a result, sometimes it can be trapped. Oh God. Second equation. And of course, the third equation will come from these torques. Torque produced, now we're looking at the pulley. Torque produced by this force, positive or negative? Of course, positive, because it tries to, and in this case, it will also be turning that way, right? Not just tries. So it will be tau 1 positive. This torque tries, actually, this torque, yeah, tries. It will try to turn, but actual motion will be that way. Minus tau 2 equals moment of inertia times angular acceleration. This will be the third equation, but we need to calculate explicitly what are these torques. We need to get these torques. All right? Now let's do it. Torque 1. What will be the torque 1? The magnitude. Directions are already there, plus minus is in front, right? What is the value of the torque? We can use the same trick, you see. R perpendicular times F. F, here our tension, this is the line of force, right? And R perpendicular is just a radius. It's just a radius. Okay, let me write here. So this will be r perpendicular for the first mass, and it is equal to radius. Okay, let me write it here. R perpendicular for the first tension times tension itself. You see that trick, r perpendicular times force, it's quite useful. Of course you can use still r, f, sine of angle, but if you remember this, right, it can save you a couple of minutes. So, and r perpendicular is just r capital times t1. So now the second torque, exactly the same, right? R perpendicular for the second mass, it will be r capital. Let me put it right here. So now this is r perpendicular for the second tension equals to radius of the disk. Hoop. It's a hoop. Right. So r perpendicular for the second mass times t2 equals r t sub 2. So these are absolute values of these two torques. One is positive, one is negative. Okay, so now I can write this. So it will be RT1 minus RT2 equals I alpha. So that's my equation number 3. I just applied universal law for our system. Because it's universal, we can apply it for any system at any moment of time. Now, in these 3 equations, how many unknowns do we have? 2? No, more. Be greedier. First, acceleration. Tension 1. Tension 2. What else? Angular acceleration, alpha. So right now we have 4 unknown, 3 equation system is not complete. From the mathematical point of view, you cannot solve it. So what else can be used? We used it, we had similar problem in your homework and we solved it in class, but this mass was not hanging, but this mass was on the table. You remember the problem? We had a pulley, we had a table, one mass was hanging, the second mass was on the table, and the whole thing was moving this way. It's exactly the same problem, just mechanics slightly different. Not mechanics. The system slightly different. What else can be used?
Alpha is equal to A over radius.
Over. I prefer to multiply. I don't like to use it. Yeah, absolutely. Equation which links, actually I should have written it in the exam, in this review. Equation which links translational motion and angular rotational motion. A equals alpha times R. Equation which links translational motion and rotational motion, assuming that there is no slipping in those parts where these motions are connected. And in this case, of course, we will assume that cord does not slip over the surface of the pulley. Right. So that will be the equation number 4. Okay, let me add this. And now equation number 4. Okay, that was for this equation, and now equation number 4. A equals alpha times R. So that is our equation number 4. So now the system is complete. At this point we can say, okay, physics is over. Now it's just the algebra of solving 4 equations with 4 unknowns, plus equations are trivial. First of all, we just get rid of this alpha using equation number 4. We will have 3 equations. And then I will extract T1 from here, T2 from here, plug it in this equation, we will be able to get acceleration. So this system shouldn't scare you. This system is trivial for your level. Okay, so now let me continue. I will just rewrite this equation, this equation, this equation, using that. I will just plug alpha into here. I will have 3 equations with 3 unknowns, and then I will solve it. So it looks complicated, but if you follow the strategy, step by step, you should be able to pull this problem. Okay? Don't try to get the answer immediately. If we see that you completed free body diagram, already tons of points. If you start applying Newton's second law, you might have some minor mistakes. You can make some minor mistakes here and there. Okay, maybe 1-2 points minimum, maximum. I mean subtraction, right? But if you see that you have a strategy, if you follow this, okay, you will get maximum almost everything. Okay, so now let me do this. M1G minus T1 equals M1A. Second is T2 minus M2G equals M2A. Second equation. And now I will rewrite R can be factored out, so it will be T1 minus T2 equals I. And instead of angular acceleration, I will use our linking equation. Equation which links translational and rotational motion. I will use over here. So it will be A over R. A over R. So 1, 2, 3, right? 3 equations plus 3 unknowns. So the rest is algebra. We applied all physical concepts. All physics is here now. So now it's just solving a system of 3 equations with 3 unknowns. You can use any method you want. I will just get T1 from here, as I said. T1 will be equal, it will go to this side. This goes to that side. It will be M1G minus A. From the second equation, I will get T2. I'm just eliminating variables. T sub 2 equals, it stays here, this term goes to this side, and I will factor out M2, A plus G. And now I will take this R and bring it over here. This R, so I'll have only difference between tensions, right? So it will be T1 minus T2 equals I A over R squared. So now we'll take this tension, plug it here, this tension plug there, and we'll have an equation, one equation with one unknown. Such a silence. Are you terrified by this system?
Yes.
No. You shouldn't, right? It's not. These are not differential equations, right? These are simple set of linear algebraic equations, right? You just.
You got to go for the ladder.
Ladder is not easy. It's not that simple problem. But something like that will be in the exam. Even if you can write all these equations again, it will be, I know, 80% of the problem. Okay, so now let me continue this equation number 3. So now I will plug T1 and T2. It will be M1G minus A. So this is T1. You see, I plugged this over here. Minus this, minus M2A plus G. So that is T2 from the second equation. And it must be equal I times, okay, just that term. I times A over R squared. So now, how many unknowns? Just one. Now just one. So it's acceleration, acceleration, and acceleration over here. So I will take this term to this side. I will just take this term to that side. This and that term will stay there. So now it will be M1G minus M2G. Minus? Yeah, minus. Yeah, it will be upstairs, so everything is fine. I thought it would pop up in the denominator. Whenever you see minus in the denominator, something is which you have to be careful. Because in that case, it means infinity is possible. But infinity stuff is usually, you have to be careful if it's true. true or not. All right, so these will be positive, these will be, both of them positive. M1A plus M2A plus IA over R squared. We're still alive, the battery is still alive. Okay, so A can be factored out, and we're done. And we're done. So now A will be equal M1 minus M2G. I factor out G. And that, all that factor in front of A will go into the denominator. What? We don't have R?
Up here, the third equation, you have R times I over minus D multiplied by R.
This?
So I basically,
Why we have R to the power of 2?
I is MR squared, right? I, the moment of inertia.
Moment of inertia I will insert at the very end.
Okay, so it's
I don't care right now, right? I just want to get the final formula. I know I can calculate moment of inertia because all the numbers are given, right?
it's MR squared, so it's simplified by
Yes, yes, of course. At the end, that's why I told at the very beginning that my R will disappear at the very end. Yeah, absolutely. So M1 plus M2, M plus, okay, now I will still write down I over R squared. Okay, and now, of course, R squared will be cancelled, right? So M1 minus M2G divided by M1 plus M2 plus M capital R squared divided by R squared. This, I need to change that. This and that gets cancelled. Okay. Again, if you get lost somewhere in this wood of three trees, three equations, right? Okay, it can happen, right? But what is important? We want to see that you are capable of writing these equations, right? All these equations. And that's where physics is. Okay, messing up with this system of three equations or four equations, okay, yeah, you can make a mistake. But that's not the most important. Okay, questions? Of course, now you can find tension. For example, now we have an acceleration. Plug it in this equation, you will get T1. Plug it over here, you will get T sub 2. Yeah. T1 and T2. Over here, this. Tau. It's a Greek letter tau. Okay, so I used these three options of calculating torques. Right? You can go RF sine theta. Actually, you can use even this formula, right? So what? Let me. This tau 1, R1, T1 sine of. What is the angle between R and T? Look at the diagram. This is R1, right? Strictly speaking, from the axis of rotation to the point where the force is applied, right? 90 degrees. Sine of 90 degrees is 1, right? And R1, yeah, that's R1, R perpendicular, right? You can use, in this case, it's simple. You can use even angle or R perpendicular. They both trivial, simple, right? Anything else? Now let's stabilize the system. So pretty much we almost went through everything except for these three conditions. And it's fresh. We just discussed a few problems in our recitation classes. And again, it's just application of these Newton's laws when acceleration equals 0. So all these conditions, this is 0, net force equals 0. Acceleration 0, net force equals 0. Angular acceleration 0, net torque equals 0. So it's just application of the Newton's second law. Again, we will just draw a free body diagram and try to satisfy those conditions. Can I erase this? Can? Good. Yeah, so the problems of this type, right, as I told you, In the class, we solved the problem when this mass was on the table, fully, the second mass. Idea is exactly the same. Write two equations, solve them. Right, or pulley, I mean the R2 machine, this mass here. This mass can be also on some inclined plane. It's exactly the same, but of course algebra will be more complicated, right? I'm nice enough not to deal with that problem. Right. But the idea is exactly the same. Okay, so now let me start erasing this. Again, so let's stabilize a sign, a straight sign, which is hanging from some beam. I think I was planning to solve this problem in our last lecture, but of course, I usually never get to that point. So I decided to solve it in the exam review session. So what do we have here? So now it's a problem about static equilibrium. The last one. Static equilibrium. Okay, so again, I will draw the picture first, then I will give you numbers, and then we'll start analyzing and discussing. So let me, we have enough space, make sure. So that is a wall. Frictionless wall. There's no friction. Oh, no, I'm taking it back. No. It must be a friction. It's in the letter usually frictionless, to simplify problems a little bit. Here, no. Just a wall. Yeah, we hit the wall. Right. So now, beam. Beam is at the angle. Length L of the beam. Right, so let me write, where should I mention? Okay. I will do it here. L. Length L. Mass M capital. Mass M capital. Of course, it's not enough to make this system stable, so we'll take a cord and connect it to this point. Let me make the wall bigger, and I will erase this. And the sign. What should I write here? Okay, no. The sign is too small. M. Then, this angle is given, theta, which is also here, theta. And this distance between these. Okay, you can think of this point as having a hinge, or we can stabilize even without having a hinge. But of course, you have to calculate properly all the forces, right? So this distance is h, and now I will give you all the numbers. So numbers are beam, 12 kilograms. Sine, oh my, sine is heavy, 21.5. Okay, usual. Yeah. M equals 21.5 kilograms. Then, length of the rod of beam, 7.2 meters. And the angle is 37 degrees. Right? So to be close. So what do we need to find? Eventually, we need to find tension in this cord, so that the system will be stable. So we need to find, no, it's not the whole thing. Now we'll have to find more than that. So tension and forces acting on this beam from the wall. In a second, when we label them, I will write what else we have to find. But for now, just that tension. Here, H. I did not write down what is H. H is this height, I mean, between this cord and the point of contact with the wall. Where is H? Where is H? H. 3.8. 3.8 meters. Okay. First question, in the problems like this, I usually ask, what are we going to stabilize? We have what? We have wall, we have cord, we have mass, we have beam. We are stabilizing the beam. We're stabilizing the beam. Because look, we just applying Newton's second law. What we dumped on this side, m times acceleration. This force is acting on that mass, which is here missing. So here we have to draw all the forces acting on this beam M capital. Stabilizing this sign is quite simple. It just means that weight must be balanced by the cord, tension in the cord. So your cord must be strong enough. So stabilization of the sign is trivial. What is not trivial is stabilization of the beam, of this rod. Because sometimes students ask me, so why I'm not drawing some force which acts on this sign, because we're not stabilizing the sign, we're stabilizing. So let me emphasize on this. So we stabilize this beam. That's what we do. So now we have to draw all the forces acting on the beam. And then we will start applying this Newton's second law with acceleration 0, preventing any possible motions or any possible rotations. Right? So now let me write all these three conditions again. Net force, okay, no. I stopped because I wanted to write x direction, but I haven't introduced x direction. So let's complete free body diagram, and then of course I will write down all those conditions. So free body diagram. Okay, let me start from this side. Mass mg, right, will be, the tension in the cord will be equal to the weight in this of this mass. I think it's obvious, right? I don't have to prove it. So now let me introduce this second tension. T1, let me label it. And of course, it is equal mass times acceleration. So that's the force, a force, acting on the beam from this side, from the side of the sign. Again, tension is the pulling force along the cord, away from the object, away from the beam. Then this cord, we don't know the tension, but we'll have to find, and of course we have to introduce it. So that's our tension. Okay, let me erase this and put a question mark over here. Then next, how can we introduce the weight of the beam? What's the trick? Center of mass. Again, center of mass, this amazing center of mass has a few amazing features. And one of them, how to calculate torque due to gravity, how to calculate the potential energy of a rigid object. Everything is about the center of mass. It can be shown mathematically. Right? I showed only how it can be done without actually deriving it. So let's say this is our center of mass. So we just draw force of gravity from that point, M capital, G. Center of mass is very, very useful. It simplifies analysis of the problems tremendously. Okay, so the last, I just walk along this beam, looking at all possible interactions. You remember forces are introduced to describe interactions with external objects. Interaction with the cord, here. Interaction with this cord, here force. Interaction with the Earth, force of gravity. And now, of course, beam interacts with the wall. Right? Of course, there will be friction. Which friction? Static, of course, static, right? If we fail one of these conditions, of course, that static friction will be transformed into kinetic friction, for example. Right? Not for example, it will be transformed. Okay, so first, friction. In this case, I think friction, direction of the friction force, I don't have to guess. We all see that the friction force must be upward, right? Must be upward. So that, which way I label it? Okay, first of all, I label this point, I think, as the point A. Yeah. Let me label this point as point A. Right, A. And I will label this force as F A vertical, A V. A because it's a point A, vertical because it acts in the vertical direction. And the nature of this force is friction. Nature of this force is friction. Then, of course, any other forces from the wall. Normal force, because this beam doesn't crash the wall. It means that there must be a normal force keeping it at the wall. So let's show this. And this force I will label as AH. H stands for horizontal. Point A, first subscript, H, because it's horizontal force. Again, the nature of this force, it's a normal force. Normal force. Nature of this force. Okay. So all the forces are here. Again, you see, I drew only forces acting on the beam. Right? Then, now of course we need to introduce coordinate system, positive direction for a torque. Again, for the torque over here, we're going to use counterclockwise, clockwise direction. For positive or negative. Right, so let me introduce, this is my y, this is my x, and this direction will be plus tau c w, counterclockwise. What's the name of the company which makes this equipment for hockey players? CCW, no? Huh?
CM.
Ah, it is CCM. Because now I looked and it looks like similar to the labels on the helmets and so on. Okay, so now free body diagram is here. So now we just need to again transform it into our equations. So net force, now I can write in the x direction must be equal 0. Second condition, net force in the y direction must be equal 0 to prevent any possibility of translational motion along the y-axis in the vertical direction. And the third condition, to prevent any possible rotational motion, torques, net torque must be equal 0 and around any axis of rotation. And we have a freedom to choose any axis of rotation. So which axis of rotation will you pick? And of course, I will, if you pick the wrong point, I will force you to change your opinion, right? As I keep saying in my classes, right, I practice my dictatorship skills, right? So, so which point should you pick? Should we pick to simplify our calculations? Of course, point. Of course, point. Of course, you can pick this point, but in that case, this torque will be 0, only one torque. If you pick this point, again, only one torque will be 0 automatically. If you pick this point, again, only one torque, 0. But if you take point A, these unknown forces, torques produced by these two unknown forces will be 0 automatically because those forces act at the axis of rotation. It's like trying to open the door by applying force at the hinge. Torque will be 0 and you will never be able to create rotational motion, which means open the door, right? So point A, of course, let's use point A. And I will put here around point A. So A is my axis of rotation. So we use our freedom. Our freedom. There is constitutional freedom of choosing any axis of rotation. Right? According to my constitution in the course policy, right? Right, yeah. It's the end of the semester. I'm getting in a better mood. There's still tons of craziness. So now, sometimes it's not that trivial to see from which condition, which condition you should start to use first, right? Again, in this case, I would usually guide you in the problem. Let's say part A, apply balance, for example, these forces, calculate that. Or start with this in part A and then part B or part C, right? So in that case, I usually try to guide you creating part A, B, C. And then it will be logical, it will be easier, right? But of course, if you're doing by yourself, right, just write down all these conditions and then look carefully which one will give you what. But of course, on the exam, you cannot afford wasting that time. Okay, so now I'm forcing you to start with condition number 3. Right? Okay, so now let's start with condition number 3. So let me separate. So this is introduction, and now condition number 3. So net torque around point A must be equal to 0. So now I will write explicitly. Then I realized this semester that some student confuses when I tell you this torque tries to create a rotation in a certain direction. So what do I mean by this? So here is axis of rotation. Basically, here is our axle, imaginary axle, right? So now, if I want to find out what's the direction of rotation created by this force T1. So what you have to do, here's the axis of rotation, so here's the axle. Forget about the rest of the system, forget about the rest of the forces except this beam and this force. Empty the whole field except for axis, beam, force. What will be the direction of rotation because of this force? Of course, the beam will be moving this way. So it means that this force tries to create a rotation in a clockwise direction. Just individual contribution from that force, contribution to the rotation. Because just some students started coming to me, so what does it mean tries to create a rotation? Because of course it tries at the end, there wouldn't be any rotation, right? We're balancing all the possible rotations, we're trying to get rid of them. But each individual forces will try. But their tries will be just balanced out eventually, right? Their efforts, right? Okay, makes sense? Clear? Because I was kind of a little bit surprised that that wasn't clear. So now I want to clarify. It's called experience, right? It's called experience. After listening to your questions. So now, so torque created by force T1, positive or negative? Negative. Because again, it tries to turn the system in a clockwise direction, which is according to our convention is a negative direction. So I will write, so minus tau of T1. You know what, since it is equal to mg, let me just use m small g. I know, I like this way. Minor compulsion. Then, torque created by this tension T. Positive, of course, right? Because now again, forget about the rest except this force, this beam, and this axis of rotation. First, it will try to turn the system in a counterclockwise direction, so it's a plus tau T. Next, usually I start from one end and start moving continuously, so I wouldn't forget any of the torques, any of the forces, right? Because if you start picking them randomly, chances that you can forget something increases. Then, weight. Positive or negative? Of course negative, right? So minus torque tau, weight letter tau, created by weight, by the weight of the beam. In these two guys, 0. Both of them 0. I will write again, but you don't have to write. And I will dump them immediately. Tau AH plus tau AB and 0, 0, because we picked axis A as an axis of rotation, as our axis of rotation. Right. And of course, don't forget to equals, it is equal to 0, otherwise it looks like a beheaded equation. Right? It looks very, very strange. At least for me. So now let's write all these torques explicitly. Usually this is the most difficult part when the question comes to torque calculation. Let's start with mg small. And I'm going to use again these tricks. You see this circle. What is R perpendicular in this case? So in this case, you draw the line of force and see what is the shortest distance from the axis of rotation to that line of force. We're talking about this m small g. It means that I'm talking about this line of force. So this is my line of force, mg, right? Line of force. And what is perpendicular distance in this case? From the axis of rotation to that line of force. So I'm talking about this distance, right? From the axis of rotation to this line. Shortest distance, perpendicular distance between the line of force and the axis of rotation. Because I drew it slightly lower, it should be over here. I know that I'm going to have another line, so I'm trying to free some space. So that will be my R perpendicular for the force mg, upper script mg. Do you see it? Right? Makes sense? Following? Okay, cool. So now, as a result, and all the signs are here, so now it's just absolute values. So it's mg. Oh, let me write first R perpendicular of mg times mg itself. Okay, so R perpendicular. Yes, so what will be R perpendicular? Let me label points so that it will be easier for you. Let me label this point as B, this point as A, B, C, D. C I want to preserve for center of mass. So if you look at this triangle ABD, can you see what will be? It's a L times cosine of this angle, right? Let me write this in the explanation box. So look at the triangle ABD. So in this case, AD equals to AB times cosine of angle, which is given. So AD is our length of the rod. This is R perpendicular for mg. So it is equal L times cosine of theta. Is it clear? Just simple properties of a right triangle. So it will be L mg times cosine of that angle. So that's the magnitude of the torque. The sign we already decided that it will be negative. So now next, torque. Which one? Create. Let's take care of this because it's very similar idea, right? So let's take care of m capital G again. It will be R perpendicular m capital G times the force itself. The same idea. Line of force. This is my line of force, right? And again, what is the shortest distance, which is perpendicular distance, from the axis of rotation to this line of force? Of course, we're talking about this, right? Let me over here. So it's R perpendicular for m capital G, which is, R perpendicular. Okay, so now let me again write explanation box over here. And I need another point. Let me introduce this point as point A, B, C, D, E. Point E, let's say. So now we have to look at this triangle A, and I need another point. Let me label this C. C, center of mass. So A, C, E. Again, it's a right triangle. So triangle A, C, E. So it will be, we need AE equals to AC times cosine of the angle. Just silence, this kind of worries me. Worries me.
I'm
You
sure you were
understand?
more worried.
Huh?
I'm sure you were more worried.
Yeah.
But is this clear? All this geometry? Okay. Because it can be either trivial for you or something outside of complete of you. Only these two cases I can expect this silence. This silence. So AE, it's R perpendicular of m small g equals to L. L over 2, right? Because we are talking about the center of mass, so this distance is L over 2. Let me emphasize that this is L over 2. So it's L over 2 times cosine of angle. Yeah, this problem's more complicated than what we had at the very beginning of the semester, but that's how it works, right? At the end, most complicated stuff. So we'll have L over 2, m small g, cosine theta. We're almost done. Another 5 minutes and we will call it today, right? So now let's calculate this torque. So you see one by one. You know what? I don't want to go below because it's difficult for you to see. Right, so torque created by tension. Again, I will use the same trick, R perpendicular times full force. R perpendicular for the tension times the tension itself. This is a little bit more complicated. So, line of force. Here's my tension. So I will draw a line of force in order to find R perpendicular. And what is R perpendicular? Huh? In this case, actually, I thought it would be more complicated, but it's actually easier. H. Of course it's H. In this case, it's H. H is given. That's why it was given, because we will need it. So, in this case, it's just H times T. You see, this is line of force. This is axis, so we're interested in this distance, and that is H. Let me write over here now add, it's R perpendicular for the tension